Hello everyone. Thanks ANRF and IIT Mandi for this initiative and opportunity to present our research. On behalf of MS Regist Lab, we will be presenting the work done under ANRF SERB sponsored project that investigates the impact of climate change on the lifetime vulnerability and resilience of aging highway bridges. Bridges are one of the most critical lifeline structures serving as a vital links in transportation networks. They connect communities, support economic activities, and require significant capital investment. Therefore, ensuring their safety and functionality is essential for uninterrupted transportation and societal resilience. Throughout their service life, bridges are continuously exposed to environmental stressors such as corrosion, flooding, and scour, which progressively deteriorate critical components and reduce structural capacity. Moreover, many existing bridges were designed using antiquated design standards, making them more vulnerable to natural hazards, including earthquakes. Therefore, assessing their lifetime vulnerability is essential for ensuring long-term safety and resilience.
The need for timely maintenance and rehabilitation is particularly critical in India. According to IBMS, more than 200 bridges are over 75 years old and 147 are already in critical distress condition. Furthermore, flood and scour account for over half of all bridge failures, while earthquakes contribute nearly 27%. These statistics clearly highlight the need for lifetime vulnerability assessment and effective rehabilitation strategies for aging bridge infrastructure. This image shows some major bridge failures caused by natural hazards across the world. Most of these failures are associated with earthquakes, floods, and scour, often acting on already deteriorated bridge systems. In addition to aging and natural hazards, climate change introduces an additional long-term threat to bridge infrastructure. Rising global temperature accelerate corrosion of RC components, while changes in rainfall patterns increase the frequency and severity of floods and storms. As a result, increasing bridges are expected to deteriorate faster and become increasingly vulnerable throughout their service life. To capture these future changes, climate projections are represented using latest CMIP6 shared socioeconomic pathways or SSP scenarios. These scenarios describe different greenhouse gas emission pathways and their corresponding temperature projections. In this study, these climate projections are incorporated to evaluate how future climate conditions influence bridge deterioration and lifetime vulnerability. Climate change accelerates chloride-induced corrosion in RC bridges by increasing temperature and environmental exposure. Corrosion causes rust formation, cracking, concrete falling, and loss of reinforcement, which leads to reduction in strength and ductility. Consequently, when an earthquake occurs, these deteriorated bridges becomes much more susceptible to severe damage or even collapse. To quantify the effect of climate change, temperature and relative humidity correction factors are incorporated into the corrosion initiation model. The results show that average corrosion initiation time reduces from 31 years under normal condition to around 22 years after considering climate change effects, which indicates significantly accelerated deterioration. After corrosion initiation, the corrosion rate increases progressively under climate change, leading to greater reinforcement area loss and continuous degradation of both steel and concrete properties. Consequently, the bridge experiences a substantial reduction in its load carrying capacity and seismic performance.
Climate change not only accelerates corrosion but alters the hydrological cycle by increasing extreme precipitation and flood intensity. These higher river discharges result in deeper foundation score, reducing foundation stability and causing larger deformations. Consequently, riverine bridges become significantly more vulnerable to structural damage and failure during extreme events. Score can be evaluated using two approaches, as a time-dependent process over the bridge service life or under an extreme flood event. In this study, the time-dependent score depth was estimated using historical discharge data, while the effect of climate change was incorporated through future discharge projections for 100-year design flood. As shown in figure, increasing river discharge under future climate scenarios result in significantly greater score depths, making bridge foundations more vulnerable. Till now, we have seen how climate change accelerates corrosion deterioration and leads to deeper foundation score. To evaluate the combined impact of these climate change-induced hazards on bridge performance, we have developed a high-fidelity finite element model of a typical highway bridge in open seas. The model incorporates detailed nonlinear behavior of bridge components, including bearings, abutment, foundation, and the effect of corrosion and scour. Finally, the developed numerical model was validated against experimental studies, providing confidence in simulated structural responses.
After developing the numerical model, we investigated the effect of climate change accelerated corrosion on the service load reliability of an RC bridge in Gujarat, India. The result shows that corrosion alone reduces the bridge shear capacity by about 33% over its service life, whereas incorporating climate change increases the reduction to nearly 57%, indicating much faster deterioration. A similar trend is observed in service load reliability. The bridge reaches an unfit for use condition after about 83 years under corrosion alone. But climate change further reduces the service life by approximately 18 years, highlighting its significant impact on bridge durability. Next, we investigated the combined effect of climate change, accelerated corrosion, and earthquakes on the seismic vulnerability of aging bridges with the help of seismic fragility curves. The result shows that compared to the as-built bridge, the 75-year corroded bridge exhibits higher seismic vulnerability, which further increases under future climate scenarios, with the highest probability of failure under the SSP5 8.5 scenario. Similarly, the climate change accelerated corroded bridge experienced greater functionality loss and lower resilience, indicating a significant decline in post-earthquake performance and recovery capacity. Next, we investigated the impact of climate change-induced scour on the seismic vulnerability of riverine bridges. The result shows that the seismic vulnerability increases significantly under future climate scenarios. Compared to the historical condition, the bridge exhibits a higher probability of failure under both SSP2 4.5 and SSP5 8.5, with the highest vulnerability under the SSP5 8.5 scenario. Likewise, the increased core depth due to the climate change significantly reduces the seismic resilience of the bridge. Finally, we investigated the combined impact of climate change, accelerated corrosion, scour, and earthquake on the seismic vulnerability of bridge systems. Unlike previous study that considered these hazards independently, this work developed time-dependent multi-hazard fragility and resilience curves by incorporating the coupled effect of corrosion and scour under the changing climate conditions. The result shows that the bridge failure probability increases progressively over the service life as corrosion and scour intensify, resulting in greater post-earthquake functionality loss and a significant reduction in seismic resilience. So far, we have seen how climate change accelerates corrosion and scour, increasing the seismic vulnerability of aging bridges over the time. However, vulnerability assessment alone is insufficient. Effective mitigation strategies are also needed. Seismic retrofitting is a practical and cost-effective solution, but its effectiveness depends on the retrofit configuration and intervention timing. Optimizing both is essential to maximize safety, extend service life, and improve sustainability. Therefore, we next investigated suitable retrofit strategies to mitigate these adverse effects. First, we evaluated the effectiveness of FRP jacketing in improving service load reliability. The result shows that the strengthening of the bridge girder with FRP delays deterioration and extend its service life. FRP jacketing was then applied to the bridge pier, significantly enhancing lateral load capacity and reducing the seismic fragility. Finally, REPREP was adopted to mitigate climate change-induced scour, improving foundation stability and lateral load resistance while reducing the seismic vulnerability of the bridge. Finally, we evaluated the effectiveness of these retrofit strategies in terms of seismic risk and resilience. The result shows that the timely FRP retrofitting reduces the seismic risk by enhancing the structure capacity of the bridge, while RIPRAP improves foundation stability and seismic resilience under climate change conditions. Overall, both strategies effectively mitigate the effects of climate change by reducing bridge vulnerability and risk while enhancing the resilience.
The outcome of this research have been published in several reputed journals and international conferences in the field of structural and earthquake engineering. Finally, we would like to express our sincere gratitude to the ANRF for their generous financial support which made this research possible. Thank you everyone for your kind attention. This research represents the collaborative efforts of the MH Resist Lab at IIT Mandi. If you have any question or would like to discuss potential collaboration, please feel free to contact us using the details provided. We would be delighted to assist you. Thank you.